Today we're going to be talking about waves. Let's begin our TNOTES. When we're talking about waves, we have to talk about what a vibration is. And a vibration is simply just the repeating back and forth motion. We know that things move, right? Atoms jiggle around, they wiggle back and forth, and this back and forth motion is called a vibration. Also, it is called an oscillation, so you might see this used interchangeably. The back and forth motion of specifically a swinging pendulum is known as simple harmonic motion. And here's an example of a pendulum that is swinging back and forth. Let me show you an example of simple harmonic motion. Here's a pendulum that has a pen attached, and the pendulum is swinging back and forth. If the paper on this conveyor belt is not moving, then we know that as the pendulum swings back and forth, you would just create a straight line. If the person begins to roll and spin this part right here so that the conveyor belt moves the paper and the pendulum is still swinging, you would create a wave, a sine curve. So you would actually create a motion that looks like this. Over here on the right-hand side, you'll see that there is a spring with a mass hanging on the end, and if it is pulled, it would allow the ball to move up and down, and if there is a pen attached to that, and again, you'll see a roll of paper, if the roll of paper is moving, then what you would experience is, again, the drawing of a wave, of a sine curve. So let me show you what that looks like in action. So here we have a spray paint can attached to some long springs. There's the roll of paper, and we have a coil of string that we're going to pull in order to rotate the paper or to move the paper. Here we have the man who's going to set up the spring. And notice how there's an up and down action right now with the vibrations. However, if you pull the paper, it would create this simple harmonic motion, which is characteristic of how waves move. This creates what we know as an S shape or a sine curve, and this is the shape of a wave. What is a wave? Well, a wave is just a vibration or a disturbance, and that disturbance and vibration they move through a medium, which could be a solid, a liquid, or air. Waves do not transport matter. This is very important to note. Yes, that vibration is moving from one place to the next. However, it does not take matter with it. For example, if you look down here where there is the line, this is the beginning of the wave. There's a rubber ducky sitting right in the water, and this disturbance, this wave, starts off where the line is in the first picture, and then as it moves through the water, notice that the duck has not moved. It might go up and down as the wave goes through, and this is T2, so this is at whatever time where the wave has now progressed to this point, and then the wave progresses out further, and the duck is still in the same place. So the wave transports itself through the liquid, however, it does not take the matter with it when it moves. Let's talk about some examples of how waves travel. Light travels from one area to the next, and it goes through the air. Depending on the kind of light, then you will actually experience a different kind of wavelength. What you notice here is there's radio waves, microwaves, infrared rays, visible light, ultraviolet, X-ray, and gamma rays. This is from the lowest frequency all the way to the highest. So this is just an example that light travels in waves. Sound also travels in waves, and here is an example where the sound is traveling through the air to where the person can hear the vibrations. And if the vibrations that are coming from the speaker were drawn, it would show that the frequency and the wavelength of the waves would look like this. The same here with the animal that is barking, the dog that's barking here. The sound is going towards the person who can hear the sound. However, it would also come out looking at like this in its oscillations. Waves, known as disturbances, can also travel through water. And we see that here with the disturbances of the waves looking concentric here. And then, of course, there's some disturbance between the two different sets of waves that are interfering with each other. But these are just some examples for you to know that waves can travel in water. Waves that move through the Earth's crust are called seismic waves. And this is an example of waves that are going through a solid medium. And depending on how the wave is traveling, it creates different frequencies and wavelengths, as seen here. We're not going to go really into the depth of learning about each of these different kinds of waves. I just wanted you to know that there are waves that can go through solid matter, and this is one example. Let's take a look at the parts of a wave. Here's an example of the simple harmonic motion. And there is a ball attached to a string and it is bouncing up and down, so it's vibrating up and down. It has a pen and the paper is being pulled across to the right. Therefore, it is creating this sine curve that we know is a wave. The crest, which is right up here, is known as the top of the wave. And it is the highest points of the wave. The lowest points of the wave are called the trough. And that is located here, it is also here, so every low point is called the trough. What you will notice is that there's a dotted dash line here, and that separates the top part of the wave from the bottom of the wave. It is equidistant in both. So what you'll have is you have something called the amplitude, and from the equilibrium point, the midpoint of the wave, up to the crest is called the amplitude. It is also from the middle part of the wave to the lowest point, the trough, that is also called the amplitude. So it is the middle to the high point, the crest, and the middle to the low point, which is the trough. That is the amplitude. Notice up here, wavelength goes from crest to crest. A wavelength can also go from trough to trough. But notice here that the wavelength goes from this point here to the same point in the next part of the wave. The wavelength is always going to be from the same point of the wave to the next point of the wave that is in the same spot. And it is denoted with lambda as being the symbol. Now that you have the diagram for the parts of the wave and they are all labeled, let's go into each part and just write down what we talked about on the diagram. That way you can reference back if needed. The amplitude is the height of the wave. It is from the midpoint to the crest or from the midpoint to the trough. The higher the amplitude that you have, the more loud something is, the higher the volume. So if you've ever heard of amps, the more amps means the more loud something is. And this is an example of a higher amplitude versus a lower amplitude. So all it is the height changes, creating a higher volume. The wavelength is the measure of one complete wave, and it is denoted by lambda, which is this character right here. Remember that it is from the crest to the crest. It can be the trough to the trough, or it could be at any point so long as it is the same point on the other part of the wave. A period, which we did not place on that diagram, is denoted by the large letter T. It's the capital T. And it is pretty much the time that it takes for one complete cycle of a back and forth motion, of a vibration. It can be, for example, crest to crest. That would be a period. So that would be a complete cycle. Or it could be from down below, from trough to trough. This is related to frequency, which we'll talk about next. Frequency is denoted by the cursive lowercase f. And when you hear the word frequent or frequency, you always think of how many, how much, how often, right? So when we think of frequency, we think of the number of cycles. It is how many back and forth motions occur in a certain amount of time. And usually we time it by how many cycles are in 1 second. We measure this frequency in what we call hertz, denoted as Hz. 1 hertz is 1 cycle per second. The higher the frequency, the higher the energy, the higher the pitch. So, for example, here we have a little picture where the wavelength is long. This is going to create a low frequency. You're going to have fewer cycles within the same amount of time than if you look down here, we have more cycles, shorter wavelengths, within the same amount of time, the time being 1 second. We would call this a low frequency wave. We would call this a high frequency wave. Here's an example. If I had 1 cycle in 2 seconds and I want to solve for frequency, frequency is, remember, how many cycles in 1 second. All I would need to do is divide how many cycles by how many seconds, and that would give me per seconds. So when I take 1 cycle divided by 2 seconds, I would get 0.5 hertz, which means that I have half of a cycle, half of a motion of a full wave in each second. Another example is if I had 8 cycles, 8 back and forth motions in 2 seconds. That would give me 4 hertz, which means that I have 4 back and forth motions, 4 full cycles in every second. And we can tell that the higher the number, the higher amount of motion, how many cycles I have per second. So 4 hertz is much higher than half a hertz. There is a relation between frequency and period. They are the opposites. They are the inverses of each other. So frequency is denoted as the little f here, and that equals 1 over the period. Whereas if you solved for t, then it would just create t equals 1 over the frequency. If we know the frequency, we can solve for period. And likewise, if I know the period, I can solve for frequency. So there is a relationship between frequency and period, and these are the 2 equations. Here is an example. If you have a wave that completes 1 full cycle in 0.67 seconds, you can find the frequency of the wave. All you need to do is plug it in, so we know that the period is 0.67 seconds. We have 1 divided by the period, which is 0.67 seconds, and we get a total of 1.5 cycles per second, which is 1.5 hertz. If we know the wavelength and the frequency, we can figure out how fast the wave is traveling. We have an equation here that is speed equals lambda times frequency. And remember, lambda is the wavelength. Here's an example. The wave speed does depend on the medium that the wave is traveling through, so just keep that in mind. But let's go ahead and do an example. If a large slinky, which is like a coiled metal toy that kids play with, if a large slinky has a wavelength of 0.95 meters and a frequency of 2.2 hertz, how fast is the slinky traveling? So go ahead and try to solve this and then start up the video again to check your answer. Alright, so we just know that we need to plug in the wavelength and the frequency, and we multiply those 2 numbers and we should get the velocity, which should be in meters per second. When we plug that in, we get 0.95 times 2.2 cycles per second, gives us a total of 2.09 meters per second, which is, after significant figures and rounding, we get 2.1 meters per second. All right, that's everything for today. Thank you for watching. Have a great day.